So let me remind you of what I said last week. I talked about what gravitational waves are in general. I talked about where they come from, what they tell us about the sources, and I talked briefly about why they're so difficult to detect. Today, I want to talk about how one actually does detect a gravitational wave in the context of the Laser Interferometric Gravitational Wave Observatory called LIGO. And I'll talk about our golden event, our discovery back in September of 2015. And I'll talk briefly at the end about the future, what else we think we might see in the coming years. You'll notice that the title of the talk has changed. It used to be, was Einstein right? Well, yeah, he was right. Okay, so as a quick reminder, we say that space is warped by mass. An object that's very massive and compact like our sun is going to warp the space around it. The Earth travels around the sun because it feels this warping of space. It's constrained by space itself to go in a circular path. And if you imagine two very compact objects like two neutron stars or two black holes that are also warping space and going in a very tight orbit around each other, they are going to swirl space and create gravitational waves, which become ripples by the time they reach us. So these ripples of space, which you might call ripples in the space-time fabric, these perturbations propagate in a very similar way to light. So they travel at the same speed. We think, if there is such a thing as a graviton, apparently it's massless, just like the photon. We think there are two independent polarizations, just like light, except the polarizations are a little bit different in their nature. So, for example, if you had a ring of test masses that are feeling a gravitational wave, they start off as a circle, but at one moment in time, they feel a stretching vertically and a compression horizontally. And then half a cycle later, it's the opposite. They feel a stretching horizontally and a compression vertically. That's a quadrupolar deformation. It's characteristic of gravitational waves. That's one polarization, which we call the plus polarization for obvious reasons. And then we have the cross polarization, where we essentially take this same pattern and rotate it 45 degrees. And these are the kinds of polarizations we'd like to be able to detect with our detectors. All right, so how do we describe the strength of a gravitational wave? We do so in terms of its fractional change in distance, which we call the strain. Let me show you a graduate student's depiction of this. It's been magnified by about 20 orders of magnitude. But it shows you this ring of test masses that are feeling some exposure to gravitational radiation. They are stretching this way and compressing and vice versa along the vertical and horizontal axes. And what we do is we measure this change in the length and divide by the nominal distance that this object was from some other test mass. And we say that the change in L is equal to this dimensionless strain times the length L. So if you're trying to measure h of t to good precision, it helps to have a very large L so that you can get good lever arm on h itself. So how do we actually detect our gravitational waves? If the wave amplitudes were large, it would be really easy. So if we had really gigantic gravitational waves, in case you blinked, let me do that for you again. I don't have the animation skills of a graduate student, so this is my attempt at an animation. There we go again. So that's a gigantic gravitational wave, enormous distortion. All right. Unfortunately, nature doesn't give us such giant waves. We expect dimensionless strains at the level of 1 part in 10 to the 21, a billionth of a trillionth. Okay. So how do you detect such a thing? So there are a number of methods have been tried over the years to do this. One method is to use very low frequencies, to look at low frequencies, by tracking very distant spacecraft signals, to look for a modulation due to a distortion of space between us and that spacecraft. You search for modulation characteristic of gravitational waves. Similarly, if you look at pulsars that are all over our galaxy in different directions, you can look for a characteristic quadrupolar distortion of space that affects the timing of the pulses that we see from those pulsars. I talked a bit about pulsars last week. So those are potentially another way to detect gravitational waves. So far, none of these searches has been successful, but perhaps in future years they will see some effects. Now here on the Earth, we can look at higher frequencies. One way to do it would be to look for energy deposited in a suspended resonant bar. I'll talk more about that in just a moment. Or to look for a disturbance of a laser interferometer. So before I talk about the LIGO method using a laser interferometer, let me just spend a few slides talking about suspended resonant bars. This was the start of the field. So here's the basic idea. Imagine you have some big aluminum bar that is suspended by a wire, so it's somewhat isolated from the ground. I'll talk more in a moment about why that's helpful in general. And imagine that you have a gravitational wave that comes along and it perturbs this resonant bar. You can think of the two halves of this bar as it being like two masses on a spring. And there's a certain amount of elasticity in that bar. And if a gravitational wave comes along, it's going to, in some sense, ring the bell. That's the basic idea. And it might surprise you that an ordinary, say, cylindrical bar could actually behave like a bell. Normally we think of bells as being these very particularly shaped objects, like the Liberty Bell, but in fact, a symmetric piece of metal, like this aluminum rod here, can behave in some sense like a bell. So let me show you how that works. Here I have a glove with some rosin on it, which allows me to excite vibrations in the rod. And it's sort of suspended by my fingers. Not as well as a string, but it gives you some isolation. So what I'm going to do is create a sound wave inside the bar. It's a vibration of the bar. Let me move so everyone can see me. And let's listen to the quality of the sound. It might surprise you. Okay, so that is an aluminum rod, a very simple aluminum rod that hasn't had any particularly fancy mechanical applications done to it the way you might with an alloyed metal that you're going to use for a gravitational wave experiment, and yet it has a mechanical cue that we call it, a resonant behavior that's actually quite good. So the idea is if a gravitational wave came along, it might excite the natural resonant frequency of that rod, and in that process, it would create slight vibrations that can be picked up with a piezoelectric transducer. That's the basic idea of one of these rods. Now, or I should say cylinders. So if a gravitational wave comes along, it rings the bell, it creates that resonant phenomenon, and you could hope to detect that by having very sensitive electronic devices. That was the basic idea of Joe Weber, who was really the father of experimental gravitational wave science. So he built a bunch of suspended bars over the years. This is one of them. This is around 1965, after he'd gone through a few iterations already. And you can see he's applying piezoelectric transducers to the waist of this rod to try and detect gravitational waves. Now, the problem with this kind of a technique is it's inherently narrow band. It's going to pick up the energy in a gravitational wave that happens to match the resonant frequency of the cylinder. But that doesn't give you very much information about what's happening outside of that band. These cylinders were typically running at around 900 hertz. That was their natural resonant frequency just because of the dimensions of these objects and their densities. And so if a gravitational wave, for example, from a supernova, came along and had a lot of energy right around that frequency, then you might hope to detect something. But these are not good at detecting waveforms, reconstructing a waveform like the ones I talked about last week. For that, you might want to have a whole xylophone of these things with different sizes and perhaps even different densities. So it's one way to do it, but in fact, it doesn't really work well enough. It was almost good enough, but not quite good enough. Here are a number of bars that were built over the years. They were built to run at low temperatures to reduce the thermal noise, which is important. And it was a very ambitious effort over decades to try and make these bars better and better and better. And in fact, there are a couple of them still operating. They operate in what's known as astrowatch mode in Europe. The idea is that we're not always running our laser interferometers. If a supernova happened in our galaxy while we happen to be turned off, it would be really unfortunate if no one detected that gravitational wave. So there are a number of bars that try to run as much as they can during day and night. All right, now let me go back to this other method, suspended interferometers. First, let me talk about what an interferometer is. So we're using laser light, which are electromagnetic waves. And you may recall from elementary physics that when you bring together waves, you can have constructive interference if the crest of this wave lines up with the crest of that wave. If you have the crest of this wave lining up with the trough of that wave, you get complete destructive interference. And in general, you get something in between. Okay, so an interferometer is designed to exploit that. You can see the same effect here with a couple of water ripples in a pond. You can see that where these two wave patterns interact with each other, you see enhanced wave motion, and you also see suppressed wave motion. The crest and the trough sometimes interfere destructively, sometimes constructively in that snapshot. All right, so this idea is exploited in interferometers. And let me demonstrate this with sound waves. So right here I have two speakers that are emitting the same tone, but they're separated from each other. Okay? And what I'm going to do is turn on the tone, like so. Maybe crank the amplitude up a little bit. I'd like you to plug up one ear, like so, and move your head around. You should be able to detect constructive and destructive interference. You're hearing, I should say, a pattern of interference between these two speakers that are generating the same tone, but you're at different distances from these two speakers, so you get this interference pattern. Okay, I'll spare your ears. Okay, so that's an example of interference in the audio band. And this is an idea that you can exploit with what's known as a Michelson interferometer. Now, this is the famous Michelson-Morley experiment, which used a semi-silvered mirror. We use different kinds of coatings these days, but the same basic idea. We have a coherent light source, which for us is a laser, that is shined on a beam splitter. Half of the light goes through this way, half the light gets reflected that way, and in both cases, the light is reflected by a mirror at the other end of these arms. I would call this the X arm and that the Y arm. Okay, so that light comes back from the two mirrors, and depending on the separation of this mirror from that beam splitter relative to the separation of this mirror from that beam splitter, we're going to get constructive interference, destructive interference, or something in between, as we saw in that earlier diagram. Okay, so this detector we have here is measuring the light that comes back from that beam splitter. It's measuring how much light is coming, and depending on the tuning of the distances of these two mirrors from the beam splitter, we can tune that to be bright or dark. Okay, now, in practice, we tune it to be dark, and I'll explain why in just a moment. Let me demonstrate this. We have a little interferometer down here. So Michelson interferometer using an ordinary laser pointer. And let's see, I think, yeah, there you go. So that's a fringe pattern. It's a little different from what LIGO sees because it's a smaller interferometer and there's some various technical details. But the basic idea is that you could put a ironic to use a green laser pointer for this. But, okay, so I should have used a red one. But you can see that in the center here, we're seeing a little bit of a fluctuation, probably due to air currents in the room. But you can see that there's an alternation between bright rings and dark rings. Those are constructive versus destructive interference. And if you place your detector right at the center of that pattern and then tune it to be dark, then you're in good shape to detect a gravitational wave, as I'll explain in a moment. Before I do that, though, let me just point out that if I just barely touch this thing, you can easily see it. So I'm changing the length between this beam splitter and this mirror that I'm tapping. I'm changing it by a small fraction of a micron, and yet it's easily detected. So it gives you some idea of the sensitivity of a laser interferometer, even for something on this scale, an ordinary laser pointer and a very short interferometer. Okay, so that's the basic idea. We have laser light that's behaving coherently, and we can exploit that to get high precision in measuring changes in distance. Okay, so let me just point out, as a plug for the Ann Arbor Hands-On Museum, they have an interferometer, very similar to the one I just showed you, and you can play with it yourself. You can block the beam, and you can see the fringe pattern go away and come back again. Okay? This is something that was built by the museum in collaboration with our group here in order to demonstrate both interferometry and the ideas behind the detection of gravitational waves. In fact, this was such a great exhibit that LIGO asked the museum to create two more just like it, one of which is on display at the LIGO Livingston Observatory Science Education Center, another one that goes on tours occasionally with other gravitational wave exhibits. So it's a great interferometer. Next time you're at the museum, make sure you take a look at it. Okay, now let me talk about how you exploit this in detecting gravitational waves. So here's an animation that shows light traveling down the X arm, reflecting off of this mirror, coming back, joining up with the light coming down the Y arm, and the two come together, and this interferometer has been tuned so that we have destructive interference. So you don't see much brightness. You see the crests are lining up with the troughs in this picture. Now a gravitational wave comes along. It disturbs that delicate balance between the X arm and the Y arm. It allows the light to filter through. Now, it's been greatly exaggerated in this picture, but you can imagine if you have a gravitational wave that is changing the length of this arm relative to the length of this arm, that quadrupolar distortion I talked about earlier, exactly what you expect from a gravitational wave, then you're going to see this characteristic brightening and darkening of the light that hits your detector. That's what we're trying to exploit. Okay, now, I said these are suspended interferometers. Why is that? Okay, well, suspended mirrors are in near horizontal free fall. They are, in some sense, they're constrained vertically, obviously. They're being held up. They're being pulled down by gravity. They're being pulled back up by wires or fibers in this case. But horizontally, they're not really constrained much at all. So they're free to respond to the passage of a gravitational wave. So let me demonstrate why it's useful to suspend something. Here I have a little gadget where I can drive this pendulum, this little ball's hanging here on the string. I can drive the support of the pendulum. Now, the mirrors that are in LIGO are suspended as pendula. and we're trying to use the mirrors that are hanging down here to detect a gravitational wave. We'd like that mirror to be isolated from the ground. And so one way to do that is to use a pendulum. So let me show you how that works. Normally this is used in elementary classes to demonstrate resonance, and I'll demonstrate that along the way, but that's not actually the key thing I wanted to point out. So I'm going to crank up the frequency at which the top support moves. And if I hit the frequency that matches the natural pendulum frequency of this object, which just depends on the length of the string, then I can get a lot of motion. But the thing that's actually more relevant to LIGO is if I crank the frequency up, and then I see that I'm actually seeing less motion here than I am at the top. I'm getting isolation because of the pendulum behavior. It goes like 1 over frequency squared, so if this thing were going back and forth by 100 hertz, I would get something like a 10 to the 4 suppression of the motion of the bottom compared to the top. That's the basic idea. So that's the pendulum analog to what's happening in LIGO. Let me demonstrate this with another oscillator. This is a mast on spring system, where I'm going to drive this, which is analogous to that pendulum support. I'm going to drive this up and down sinusoidally at different frequencies, and then it's connected by a spring that's analogous to the pendulum motion to this other ball. So let's crank it up. Again, we normally use this to demonstrate resonance, and I will show that along the way. If I hit the natural resonant frequency of this mass spring system, I can make the bottom ball go up and down a lot. But what's relevant to LIGO is if I keep going to higher frequencies, let me damp out the ambient vibrations. Now I'm seeing a lot of motion up here at the top and only a little bit of motion down here. It's the same basic idea. I'm using an oscillation system to suppress motion at high frequencies. It's a bit like the shock absorber on your car. It's the same basic idea. When you hit a bump on the road, you have a sudden jolt to the car. You don't want to feel that, and so you have a spring system that isolates you from that jolting. Okay, now these interferometers are much broader band than the resonant bars I talked about earlier. I said the resonant bars can only see frequencies around 900 hertz, the ones that were built in practice. Interferometers have a broadband response. They can see an entire waveform over a range from 10 or 20 hertz up to thousands of hertz. And that means you could reconstruct a chirp waveform like I showed you last week for the in-spiral of 2 neutron stars coming together, or the in-spiral of 2 black holes. Okay, so the bigger the L is, the better the precision we have on h of t. And let me explain a little bit more about how that works. So is it really possible for an interferometer to get down to a level of delta L over L of 10 to the minus 21? I mean, that sounds impossible on the face of it. How in the world could you possibly do that? Let's see why it actually is feasible. Let's imagine we have a relatively simple experiment, something not much bigger than what I showed you here on the benchtop, where you have 1 watt of laser light with 1 micron, it's an infrared laser, 1 micron wavelength, and imagine it's in a 1 meter interferometer, something that would comfortably fit on a bench about like this size. That means you have about 5 times 10 to the 18 photons per second in that interferometer. That means that the fractional fluctuations during a half period of, say, a 1 kilohertz gravitational wave are about 10 to the minus 8. You're just using the statistics of having so many photons hitting your photodetector. You get a precision on the intensity of that light that goes like 1 over the square root of the number of photons that you have per unit time. And so that means you actually could get down to levels of 10 to the minus 8 just in the intensity, at least in principle. And then we can then translate that into our precision on delta L, given that we know the wavelength of our light. And that means that our precision on delta L, for this relatively simple experiment, could be as good as 10 to the minus 15 meters. This relatively simple setup. It's not easy to make it work in practice, but in principle, this could get you down to the radius of a proton. A 1 meter interferometer with 1 watt of laser power. Now, to get down to 10 to the minus 21, you need a longer L. We have 4 kilometer interferometers, not 1 meter. We have a higher laser power, and we make the laser bounce back and forth in the arms many times. So let me talk about that. So here's a cutaway diagram of initial LIGO. And the final advanced LIGO is a little bit more complicated than this, but the essence of it is still the same. We have these mirrors that are suspended as pendula, so they're isolated from the ground. We have light that comes in from the laser. It hits this beam splitter, and half the light goes this way, and half the light goes this way. Now, you might be surprised to see these mirrors here. Why are there mirrors in the way? Why in the world would you put mirrors between your laser and the other mirror you're trying to bounce off down here? Well, the idea is that if you hit just the right wavelength of your laser to match the length between these two mirrors, then you get what's known as a resonant phenomenon. You can get a standing wave pattern in which the light goes back and forth multiple times and interferes with itself constructively. It's basically the same principle that applies in a lasing cavity. An ordinary laser pointer exploits that same basic idea. So we have these Fabry-Perot arm cavities, which create optical resonant cavities, and then that allows us to make the light go back and forth many, many times, which means it feels the gravitational wave longer. It has more time to feel the presence of a gravitational wave, which takes a relatively long period of time to go through the interferometer because these are very long wavelength gravitational waves. And so you can experience the gravitational waves longer and then get more sensing of what's happening in the strain of space itself. Okay, so let me illustrate these standing waves with this string. So you have a string that is, I can vibrate at different frequencies, and I can create standing waves. You can think of these as waves that go back and forth in both directions simultaneously and interfere constructively. Let me go to, there I have what are called antinodes. There's 3 of them there. And if I go to a higher frequency, I can get 4. And higher frequencies, I can get 5, and so on. And so by tuning the frequency of the vibration, I can change the characteristic wavelength. And every time I hit a wavelength that happens to match some half-integer number of wavelengths in this length of string, I will get a resonant phenomenon. And so what we do with our laser and our mirrors is we fix the laser frequency, but we change the length between the mirrors by some slight amount. And since the wavelength is only 1 micron, it's easy to move one mirror slightly and get just the right number of half-integer wavelengths to get a resonant phenomenon. All right, so that's my string demo of standing waves that are analogous to the standing waves of laser light in the LIGO cavities. Let me show you another standing wave pattern. It's right here. So here I have a pipe I'm going to put some gas into. I'm supposed to smell gas. Okay, I smell it. Oops. There we go. All right, so now, over here I have a speaker that is going to inject a tone down this pipe at different frequencies. And I've already pre-chosen a frequency that works pretty well. And you can see, let me turn the amplitude. I can see people blocking their ears. Let me turn the amplitude down. Okay, thank you, Warren. All right, so there's a standing wave pattern. What we're seeing are standing waves of longitudinal sound waves that is analogous to the standing waves of transverse electromagnetic waves in LIGO. So it's the same basic phenomenon that you saw with the string, but it's cool to have a fire demo. This is the string. Okay. All right. Thank you. Okay, so now let's talk about LIGO itself. I've talked about the principles behind LIGO, and let's talk about the observatories. So there's one in Washington State, LIGO Hanford Observatory, and one in Louisiana. This is LIGO Livingston Observatory. They're about 3,000 kilometers apart, and that means that we expect that the waves that, gravitational waves that would hit both sites would hit within about 10 milliseconds of each other. Depending on the direction, there might be no difference in time, or it might be as much as 10 milliseconds if it came from the back end of either of these observatories. So if we observe a disturbance in these two interferometers simultaneously within 10 milliseconds, that gives us a fair amount of confidence that what we're seeing is astrophysical, not some terrestrial phenomenon. There are a few special things you have to worry about, but for the most part, this eliminates almost all of the ordinary noise sources that we would worry about that might fool us into thinking we'd seen a gravitational wave. Now, we do get a little bit of timing information from the fact that we see some time difference. That tells us that somewhere our source is on a ring in the sky that's consistent with that time difference. And we get additional information, but limited information, based on what's called the antenna pattern of our interferometers. Basically, their sensitivity to different regions of the sky that allows us to narrow down to some degree the location of the source. It would be great to have more interferometers to do a better job of that kind of triangulation. I'll come back to that in a moment. Now, initial LIGO ran from about 2001 to 2010, and it worked quite well. It got down to the design sensitivity it was meant to achieve. But the problem was that the gravitational waves we were looking for were just too weak. And that was not a surprise to us. Initial LIGO was always meant to be, in some sense, a massive pilot project to demonstrate the feasibility of this technology, of this technique of measuring gravitational waves. And then the idea was to build advanced LIGO, which was done from 2010 to 2015, and last fall we turned on. Let me just touch on a few things that changed between initial LIGO and advanced LIGO. So the laser power has been increased from 10 watts in the early days of initial LIGO to now 200 watts. We're not actually running at that power yet. We don't actually dare run at that power yet for technical reasons, but we hope to in a few years. There are all sorts of headaches that come up when you increase your laser power. But that's going to eventually give us improved shot noise at high frequencies. I talked about the number of photons per unit time limiting you. That's a limitation in high frequencies. The more photons we have per unit time, the more precise we can make our measurements. We also have higher mechanical Q test masses. That basically means that they vibrate sort of like a bell with a higher resonant quality to them. We call it the Q of the resonance. And that's good for isolating the power that we don't want due to thermal energy in frequencies we don't care about. That's the essence of it. Also, because we've gone to higher laser power, at least we plan to, we've also increased the masses. And the reason for that is that all that extra laser power is going to buffet our masses to some degree. The fluctuations in the number of photons means there's also a fluctuation in radiation pressure of light pushing on those mirrors, and that's not good. And so to reduce the effects of that, we just have heavier mirrors. They're 40 kilograms now. We also have a more elaborate isolation system from the ground. I talked about the single pendulum system that initial LIGO had. Now we have a quadruple pendulum system. This shows you one of the mirrors before it moved into the interferometer, showing you one pendulum hanging from another pendulum, and there are two other small stages of pendulum that you can't see very well at the top here. So we have 4 pendula that give us even more isolation from the ground. And then finally, we also have improved seismic isolation of the support itself. This now has a system that's not based merely on passive masses and springs. It has a very elaborate servo control system that uses accelerometers and seismometers and tilt meters and what have you to sense what's going on in the ground and to compensate for that ahead of time. And that allows us to get better sensitivity at low frequencies. Now, with those gains, what we expect by something like 2019, when advanced LIGO is fully complete, is an expansion of our range by about a factor of 10. We're improving our sensitivity to strain by a factor of 10, and since we're looking at amplitude, that means that we're seeing sources 10 times further out. So if you go 10 times further out, your volume increases by a factor of 1,000. Volume goes like the cube of the distance. That means our event rate will increase by a factor of 1,000 over what we had in the initial LIGO days, and we're already starting to see the benefits of that kind of improvement. All right, now I said earlier it'd be great if we had more interferometers. We will soon have more interferometers. So we collaborate closely with a group called Virgo that is building an interferometer, well, it really has built an interferometer, now commissioning it. They're hoping to come online later this year and take data with us in our next data run in the second half of 2016. It's not clear that's going to happen, but that's the goal, and it looks like it might be feasible. There's another interferometer called GEO that is not as sensitive as LIGO and Virgo down in the band where we care about inspiraling black holes and neutron stars, but it is actually pretty good at higher frequencies, and we use that in some sense in this astrowatch mode. We try to run GEO as much as we can when the other interferometers are down, so that in case a supernova comes along in our galaxy, we'll be able to catch it. That's the hope anyway. So GEO is something that's our fallback for when we're down. There's another detector being built in Japan called Kagra. It's under construction. It's actually built inside of a mountain. They've dug an impressive tunnel that is L-shaped. And they're hoping to come online in a few years. They probably won't get to LIGO sensitivities until something like 2019. But once they come online, then we're going to have the 2 interferometers in Hanford, Washington, Livingston, Louisiana, Virgo, which is near Pisa, Italy, and the Japanese experiment, Kagra, all with comparable sensitivity if all goes well. Now, you notice over here I've got this other thing called H2. In the initial LIGO days, we actually had 2 interferometers at LIGO Hanford Observatory, and we ran them routinely together. One of them was half the length of the other for technical reasons, but for advanced LIGO, we actually have built, in some sense, another H2. However, it's not actually installed. It's literally in crates. And the reason it's in crates is we're hoping to put it in India. And the reason we like to put it in India is that it gives us much better triangulation on sources. The further our interferometers are away from each other on the globe, the better the positioning, the localization we get on gravitational wave sources. And so it would be really nice to have another interferometer sitting here in India. And just this week, the Indian Prime Minister approved going ahead with this project. Okay, so It'll be a while, though. We're talking 2020 and beyond before it's actually operational. But it's great that we'll have that for our future. All right, now let me talk about the genesis of LIGO. So in some sense, it started back in 1972 with a report that Ray Weiss, a professor at MIT, wrote in which he analyzed the noise that would affect what he called an electromagnetically coupled broadband gravitational antenna. That's really the start of LIGO. Although there had been ideas beforehand, in fact, there had even been a demonstration of trying to use an interferometer to look for gravitational waves, Ray was the first person to really go at it and say, okay, here's what you need to do to actually make a discovery. You need to have big interferometers, like a kilometer long or more. And you need to deal with all sorts of thermal noise issues, and you've got to have a stable laser and what have you. So this is the first careful analysis of what you need to do to actually detect gravitational waves. So that was 1972. In 1989, he collaborated with Caltech to submit a proposal for the LIGO experiment. And it took a few years to wind its way through the NSF approval process, but eventually it was approved. And then in 1997, a bunch of us came together to form the LIGO Scientific Collaboration to deal with building the interferometer, analyzing that data, and getting ready to build advanced LIGO. You'll see that Michigan was part of that. So I've been in this field for a while now. Not as long as Ray Weiss or some of my collaborators, but it feels like a long time. This is the LIGO logo slide that would have been shown in 1997 had we thought to do such a thing in those days. Let me show you what it looks like today. Okay, the collaboration has grown. Okay, we're now about 1,000 people. We used to be 200 when we started this business. And that's good in a lot of ways, although I complain sometimes about having to be part of such a giant collaboration and how it's hard to get to know everyone and so on. It is good to have this kind of a depth. And this helped us to put out not only our discovery paper last week, but 11 other companion papers to go with it that exploited the astrophysics, demonstrated the capability of our detector, and just really showed that we know what we're doing. It was nice to have this kind of depth, although I still wish we were a smaller collaboration. Okay, here's our group at Michigan. This is Dick Gustafson. He's a senior research scientist who's stationed full-time at LIGO Hanford Observatory. Spends a lot of his time on commissioning work. This is his natural habitat, surrounded by electronics and a tangle of cables, which he knows how to make operate. This is my natural habitat, tethered to a computer screen. And then here are two graduate students in our group, Ansel and Orion. And then we have 5 undergraduates, one of whom didn't send me his picture. We have Pranav, Weigang, Stephen, Curtis, and Ilam. And we all do various things for the LIGO enterprise. We work on commissioning, detector characterization, and analysis. And you can see these little codes that tell you what each of us spends most of our time on. Here are some alumni from our group who are all still working in gravitational wave science. All 5 at the top, Grant, Jacqueline, Vladimir, Santiago, and Evan, earned their PhDs with my group within the last 7 years, and they're all continuing in the LIGO project at different institutions. And then there are 3 undergraduates who earned their bachelor's degrees with our group, who are continuing on in gravitational wave science, Jake, Alex, and Jamie. So we're proud that we've propagated ourselves out into the LIGO universe. Okay, now let me talk about our golden event. GW 150914, named for the date on which it was discovered. So in late September, I'm sorry, last September, not late September, we were in the final stages of preparation for the first advanced LIGO observing run, which we're going to call 01. We were in what we call engineering run, ER8. We're not very imaginative in naming our runs, as you can see. But on September 14th, we were pretty much in the final stages of this engineering run, just verifying everything was running smoothly, getting all of our software running, and not all of our back-end software, the stuff that we use to analyze the data, was quite ready yet. But the instrument was running great. And one of our online burst monitoring programs detected this signal. It was found within 3 minutes of its hitting the detector, and it immediately triggered some cell phone and email alerts. And after verifying that our instruments were operating well, the decision was made to just go ahead and declare 01 starts now. We're ready. Our instruments are clearly ready. And so we froze the interferometer and the software configurations and said, okay, we're just going to run like this until we've got 16 days of double coincidence data. Because we estimated, based on what we knew about our interferometer and about basically the statistics, that we wanted to have something like this amount of data in order to assess our background level well enough to claim that this was a real discovery. So we needed to collect a lot of data to make sure we understand our backgrounds, and so that's what we did. So to collect 16 days of double coincidence data where both Hanford and Livingston were operational took a while. It took us until October 20th because our lifetime was not great. We were having all kinds of shaking in the ground, storms in the Gulf of Mexico, storms in the North Pacific. All of those shake the ground, and they make it harder to operate the interferometers, or if you have high winds in Hanford, for example. But anyway, we eventually collected that data, and that analysis demonstrated that this signal came from the merger of two black holes 1.3 billion years ago. So I'm going to show you a simulation of what we think happened 1.3 billion years ago. And to set the stage for that, let me first talk about what a black hole does if it's in your line of sight. So pretend that we're close, maybe 1,000 kilometers or so, from that merger of two black holes. And first, let's imagine a simpler case. Here we have a picture of the Milky Way. Now imagine that you use in this case, the XXS software to simulate the lensing of light due to gravitational wave distortions from a black hole. So if you have a black hole between you and the Milky Way, it's going to distort it like that. Okay? So what you're seeing here is the bending of light around this black hole. This is not the tiny little deflection that Arthur Eddington detected in 1919 to confirm the predictions of general relativity. This is a gigantic effect. Okay? So we have an extreme lensing around in the vicinity of a black hole. So now you might try to identify what over here corresponds to what you see over here. And here's an example. These two stars, the yellowish-orange star and the bright blue star, can you see where they are? Okay. That's one place. You'll see that the black hole is roughly the center of the image. And so what it's done is push this out in this image down here. The light, in order to get to us, has had to go around the black hole, and so it appears to us to come from a different angle from where it actually is located. And you see there's other distortions. You can see this little dark structure here gets pushed into this region here. And you might ask yourself, does this pair of stars show up anywhere else? It does. It also shows up over there. The light can go around the other way, too. Okay. So the lensing around a black hole is quite extreme. You get all kinds of multiple images. You can also get what's known as an Einstein ring. You can see a little bit of that right here. This ring behavior corresponds to what is directly behind that black hole. So there's extreme distortion just around the single black hole. All right, now this kind of thing you can actually calculate analytically because it's a single static black hole. But if you want to simulate two black holes in spiraling, you have to use numerical relativity. And let me show you what that looks like. So here we have two black holes. These are, in fact, the black holes that are matched to match what we found on September 14th. So this is a simulation of that very event, where the Milky Way has been put in the background just to give you some sense of what's happening to the space around these two black holes. So let me turn on the simulation. You have to click over here to do that. Now, time has been slowed down dramatically here. There we go. You can see the two black holes. All of this takes place only over 0.2 of a second. So time has been slowed down. The two black holes are going around each other. They're stirring up the space around them. You can see that swirling because it's affecting the light that's trying to travel through that space to get to our camera lens. And the two black holes are getting closer and closer to each other. And eventually, the two black holes merge into one black hole, and then it shakes off the energy in the form of gravitational waves. So we think that's what happened 1.3 billion years ago that was detected on September 14th of last year. All right, now let me show you a different simulation from the same group. These are not Hollywood simulations. These are numerical relativity calculations based on the parameters of our event with as much precision as we think we can get right now. This is state of the art. So let me zoom in on this. We're looking at the two black holes from a large distance, about 30,000 kilometers. We'll now zoom in and take a look. And this is a different representation of the same process. So we have the two black dots representing the black holes. And then you can see the surface beneath them that represents the warping of space in the equatorial plane of those two black holes. And you can see the dimple that goes down. That's the warping. The color coding tells you how much time is slowed down relative to what it would be at infinity. And as these two black holes come together closer and closer, eventually this saddle is going to go away and the two black holes merge to become one. Now the animation is going to slow down at a critical point so you can see a little bit better what's going on. So you can see the saddle is going away, and then we're now forming a single oblate object. And I think it's going to freeze. There we go. It freezes for a moment, to show you what's happening at the point of merger. The two black holes have now come together. It still has a lot of excess energy. It's got a lot of excess angular momentum. It's going to shake off in the form of gravitational waves, which you can see propagating away as these blue and purple waves. Okay, so we think that's what happened. That's a more precise way of describing what happened 1.3 billion years ago. As I said, this is state-of-the-art simulation. This is numerical relativity at the extreme frontier. Okay. And we worked closely with them in LIGO, so they were able to provide us these animations at the time that we released our announcement last week. Okay, so what happens when that gravitational wave hits us 1.3 billion years later? Let me warn you that I'm going to show you something with a bit of exaggeration to it. So first of all, it's going to slow time down again. It's also going to increase the amplitude of the gravitational wave significantly. Oops, I didn't mean to do that. Let me go back. Okay, so you can see a gravitational wave front hitting the Earth, making the Earth. As I said, there's a bit of exaggeration. You probably don't recall any cataclysmic... There were no cataclysmic earthquakes on September 14th. So clearly this has been exaggerated. The actual distortion of the Earth's diameter was about 10 atomic radii or so. So it's been exaggerated a bit in this diagram. But to give you some sense, this is what was actually impinging upon the Earth. This is what we detected at a much smaller scale. All right, so this is what the event looked like. This is the waveform detected in Washington at the LIGO Hanford Observatory in red. And this is what was detected in Livingston, Louisiana in blue. Now what you see over here in this red trace is essentially this trace moved over and shifted by about 7 milliseconds to account for the travel time between Livingston, Louisiana and Hanford, Washington. The source was closer to Livingston than it was to Hanford, so it hit Livingston first. And it's also been flipped upside down because the two arms are rotated 90 degrees with respect to each other, which essentially makes one anti-symmetric with respect to the other. But basically, this is seeing the same waveform in Hanford, Washington as Livingston, Louisiana within 7 milliseconds of each other. So that tells us this is a real gravitational wave. What you see down here are some reconstructions of what we think the waveform looked like without the extra noise that we have in our detector, which always has some degree of noise. That's why you have these extra little squiggles here. But we think the underlying waveform looked like that. And then this shows you a spectrogram where the color intensity tells you how much power you had at that frequency at that moment in time. So here we have vertically as a frequency, horizontally as a time. And so you can see this chirpy behavior that I played for you last week for a pair of neutron stars. Here we're looking at black holes that have a characteristic frequency that's much lower than that of the lighter neutron stars. But you can see we see the same spectrogram in Washington that we see in Louisiana at pretty much the same time. So when we saw this, we just fell out of our chairs. Said, wow, that's exactly what we've been looking for all these years. We couldn't believe it was that nice. But sometimes nature is kind. All right, so I have a demo here. I have to remember which demo this is. Which demo was I going to do? Oh, yes, thank you, Monica. I need to be more specific about my prompts for myself. Okay, so this is a brand new demo. That's why I had trouble remembering it. So this is something that Warren and Monica came up with in the last week. This is to mimic the behavior of a gravitational wave that is being emitted by two inspiraling compact objects. All right, now this is a mechanical analog, of course, but it actually has some of the same flavor. It has the same flavor. Oh, here it is. That mathematically and auditorially that you would have from an actual gravitational wave. You're going to hear something that's analogous to the chirp. So let me... Okay. Thank you, guys. Our demo crew is fantastic. Thank you. Okay, so let me now play for you what this sounds like if you take the gravitational wave data channel and you plug it into speakers. and you simultaneously show the waveform and that same spectrogram. So this is another animation that someone put together. It's nice, and it's really a nice animation, but I want to warn you that it may be a little bit misleading because you'll hear the chirp twice in a row. We only got it once for each interferometer. You're also going to hear a frequency-shifted version of it, which is easier to hear the chirp from. You'll hear initially at its true audio frequency, exactly what you'd hear if you took the gravitational wave channel and plugged it into a speaker and did a little bit of, using a little bit of band equalization to suppress some of the unwanted noise. And then you'll hear the same thing shifted up by 400 hertz, which makes it easier to detect with your ears. Are you picking that up? I'm not hearing it. Let me make sure my audio's. Okay, let me try this again. There we go. That's the frequency shift one. So you can hear that rumble that's there all the time. Okay, that's not there all the time. Yeah, let me mute it. Oh boy, okay. I want to play it for you one more time, so let me mute my computer for a moment. You hear that rumble all the time. If you just listen to the gravitational wave data channel like that, you'll hear that kind of a rumble in the background all the time. It's just characteristic of our background noise. And then you hear that zoop, zoop. We'll only hear it once in reality. And then if you shift it up by 400 hertz, you can hear more clearly something that's better tuned to your own ears' reception. Let me play it for you one more time. I'll turn the... Doesn't want to cooperate. Let me go back. Okay. All right, so as I mentioned last week, you would not want to rely on your ears in the control room to detect gravitational waves, but it is cool that you could, in principle, detect a gravitational wave just sitting in the control room listening to the speaker. And that's what everyone on shift always fantasizes about doing. Okay, now, I showed you the waveform as detected by the interferometers. This is what we think the waveform looked like without the filtering of the sensitivity of our interferometer. Our interferometers are not the same sensitivity across all the frequencies, so if you correct for that, you get this kind of a waveform. And it shows you the different, this cartoon shows you the different stages that you're seeing in the waveform. So this stage is where you have two distinct black holes in spiraling. They're getting closer together here. The frequency has gone up, the amplitude has gone up a little bit. And then here, the point where you have the maximum amplitude is a point where the two black holes just start to merge. They start forming a single black hole, and then we get the final black hole and its ring down. Now the ring down is something that decays away rapidly, exponentially, and it's something that we see evidence for in our waveform, but we can't really pin it down as well as we would like. In principle, by measuring this pattern from the end spiral, we can tell what the masses of these two objects are to pretty high precision. And in fact, I'll show you the numbers in a moment. And in principle, we could also tell the mass of this final system by looking at the distinct waveform that's here. But we just don't have quite the signal-to-noise ratio we'd like to have. So although what we see is perfectly consistent with expectation, we can't quantify it as well as we would like. Now, if you look down here at this bottom graph, this is showing you in this black curve that corresponds to this right-hand scale. It's showing you the separation between the two black holes in units of the Schwarzschild radius of the final black hole. And so these two objects are coming together, and when you get down to about a little bit less than 1.5, they start merging together to form a single black hole. In that process, the two black holes are speeding up. What's shown here in green, which corresponds to the left-hand vertical scale, is the relative velocity between the two black holes. And roughly speaking, each one's going half of that velocity. They're going at roughly a third of the velocity of light just before they collide. We're talking about two objects about the size of metropolitan Detroit whirling around each other with speeds at a third that of light at 100 hertz. Okay? It's an incredibly violent process. All right, so now here are the reconstructed parameters from the system. if we look at that waveform, we can fit it to our analytic approximations to what we expect, and then we can use numerical relativity to confirm those more precisely. And what we conclude from that is that the heavier black hole had a mass of 36 solar masses, 36 times the mass of our own sun. The other one had a mass of 29 solar masses, and the final black hole mass, the one that was formed from the collision of these two black holes, had a mass of 62 solar masses. Now, does anything trouble you about that? Okay. They don't add up, do they? Yeah. So 36 plus 29 is not equal to 62. So what happened? Yeah, it went into gravitational waves. 3 solar masses got vaporized in the form of gravitational radiation. So the luminosity, so to speak, I mean, it's invisible except with something like LIGO. The luminosity was almost 4 times 10 to the 56 ergs per second. So that makes this momentarily, for about a tenth or so of a second, brighter than the rest of the universe combined in those last moments. All of the light output of all the rest of the universe was smaller than what was happening in this 2/10 of a second. Okay. All right. So let me go back to the idea of testing general relativity. So I talked last week about these various tests that have been made of general relativity. I said that those are looking for small deviations from what Isaac Newton might have predicted. Okay. So now we're looking at a different regime. The most relativistic astrophysical system we knew of until last September had a V over C of about 2 times 10 to the minus 3. That's pretty fast, and that's 20 times faster than the sun goes around the Earth. The other way around, sorry. Earth goes around the sun. Yeah, sorry, I'm in that pre-Copernicus mode today. So it's pretty fast, but still, V over C is pretty small. Now here we're talking about V over C of a third and a relative speed of 2/3. Okay, so we're looking at nonlinear dynamics. We're looking at general relativity being tested in a completely different realm, where the dynamics is highly nonlinear, and the black holes, of course, are being warped and distorted. So we've done a lot of tests based on the waveform that was detected. We checked that the waveform residuals are consistent with the noise. I showed that in an earlier graph, but didn't talk about it. If we take our reconstructed waveform out of the data and look at what's left over, it's perfectly consistent with background noise. So we think that we've got all of the information is contained in our reconstructed waveforms. We have some internal consistency checks. If we look at the in-spiral range where the two black holes are distinct from each other and compare that to the waveform once they start to merge and then ring down, we do see consistency. It's not a precise test yet, but we do see consistency. We can also look in more detail at that in-spiral range. We can parameterize that in terms of a set of coefficients that characterize the deviations of that waveform from what Newton would have predicted. And all of our coefficients look fine. Everything looks in agreement with general relativity. And we can also place a bound on the graviton mass by the fact that we don't see a distortion of the waveform from what we should expect for 2 merging black holes. So all of this confirms predictions of general relativity. We'd like to do better. We'd like to make more precise tests, but we've already gone orders of magnitude beyond anything that's been done before. I mean, this is strong field gravity, and Einstein's theory has passed with flying colors. So the outlook, how many more of these things might we see in the future? Okay. Well, based on what we saw in that first month of the 01 run that's been released so far, we've calculated probabilities for seeing more of these things in the coming years. So what's shown horizontally here is the time volume that we're expecting, that we want to sample, compared to the time volume that was collected in that first month, 39 days of data. Okay. So as we take more data, we see farther out in the universe, we're sampling more time, we should see more events in principle. And so if you look at the end of 01, we can see that the probability of seeing another event is something like 90%. Okay? And then if you look at what we hope to do in 02, then we have a pretty good chance of seeing 5 or more events. We might even see 10 or more events by the end of 02 if things go really well, if we get to the sensitivities that we really want. And by the time we get to 03, sometime in mid-2018, we could be looking at ballpark 30, 40 of these merging black holes that we've detected and have analyzed the properties of. So we'll be doing serious astronomy at that point, where we're not only just looking at one isolated event, but we're looking at distributions of masses and angular momentum and what have you. Okay, let me talk a little bit more about other sources. I've talked so far about binary black hole mergers. We also want to find binaries that contain neutron stars. It could either be two neutron stars inspiring with each other, as I talked about last week, or a neutron star in orbit around a black hole. We think that could also happen. And what's interesting about that is a neutron star is going to get ripped apart in that process. It's going to be tidally shredded by either the other neutron star or by the black hole that's orbiting. And so in that process, we should, if things go well, get some glimpse of how tightly bound a neutron star is. We cannot mimic here on the Earth the conditions inside of a neutron star. They're just outside of anything we could do in the laboratory. So we don't really understand what is inside of a neutron star. We think it's a bunch of neutrons, but we'd like to understand a little better than that. So this may give us a glimpse into what's holding a neutron star together. We also want to look for electromagnetic observations, meaning optical, perhaps radio, X-ray, gamma ray, that coincide with short gamma ray bursts, which do happen from time to time in our universe and get detected by satellites orbiting the Earth. We'd like to see a coincidence between a gamma ray burst and a gravitational wave detection. That would, of course, give us insight into the gamma ray burst dynamics. It would also give us a new cosmology measurement, because we could measure the same source completely differently, electromagnetically and gravitationally. That gives us a completely new reference point for determining distances to cosmologically distant points. And then also we can set limits on the speed of a gravitational wave compared to the speed of light. Okay. Another thing we like to see are supernovae. So a supernova are going to be characterized by something massively violent happening down at the core. We don't know exactly what. Our simulations are still having, the people who do these simulations are still having trouble making a supernova explode the way they want it to. It's actually a very difficult problem to simulate a supernova down deep. What we see right now electromagnetically is the outside of the supernova. We see the things that escape as very dense matter, the gamma rays, the X-rays, and the light, and so on. We like to be able to see down deep in the core, and gravitational waves allow us to do that. Gravitational waves pass right through that matter. They don't care about that stuff. They just pass right through. So any waveform that we see from a supernova is going to tell us what happened at the very core. And what would be really nice is if we could also detect neutrinos from the same supernova. The first neutrino observation from a supernova was done in 1987. That included a group here at Michigan that built an underwater detector that detected a bunch of neutrinos that were coincident with a supernova that was observed in the sky. We'd like to see more of those in our own galaxy or perhaps in Andromeda. They have to be relatively close for us to be able to see them with gravitational waves or with neutrinos. But that's something for the future. All right, there's also a stochastic random background, potentially, of gravitational waves from the Big Bang. We don't know if this is a good bet or not. Probably not. Conventional theories of the Big Bang suggest that gravitational radiation left over from that Big Bang are probably not strong enough in the LIGO band that we would ever see them. But there are alternative theories that predict that maybe we could see something. One thing that we are pretty confident we'll see eventually is a cosmic background radiation not from the Big Bang, but from all those black holes, way, way out there. The ones that we can't detect individually, but are so far away, but so weak that they just add collectively together to form a sort of a hazy background. In fact, that might actually be a foreground that interferes with doing a Big Bang measurement, which is not a bad problem to have, to be able to see that stochastic background from all the binary black holes merging way out there. And then finally, there's a source that's dear to my heart, which are spinning neutron stars here in our own galaxy. So these could be producing gravitational radiation that is extremely weak, 1,000 to 10,000 to even to 100,000 times weaker than the signal that we detected in September. And the only chance that we have of detecting something like this with our detector is for the signal to be on all the time. And so we spend a lot of our time pouring through the data, looking for tiny little signatures that are there all the time. And it's a little tricky because every time you look at a different point in the sky, you have to make a different correction for the Earth's motion. So that's something we spend a lot of our time here at Michigan. Okay, summary. We observed gravitational waves from the merger of two stellar mass black holes. The detected waveforms matched the predictions of general relativity beautifully, along with the prediction of a ring down from that resulting black hole. And to quote the last line of our discovery paper, this observation is the first direct detection of gravitational waves and the first observation of a binary black hole merger. So we announced this last week. I'll show you some pictures from that announcement in Washington. It was one of the happiest days of my professional career. And I'll just show you some of the people on the stage here. This is the director of NSF, Franz Cordoba. This is Dave Reitzle, who is the director of LIGO Laboratory. Gabi Gonzalez, who is the LIGO Scientific Collaboration spokesperson. And then here you have Ray Weiss, whom I mentioned earlier, and Kip Thorne, whom you may also have heard of. He's He's the person who helped make Interstellar, the movie, possible. And he's done a lot of other things to popularize general relativity and gravitation. Here's Kip here. Here's Ray demonstrating the warping of space-time with a green mesh. And I can't help but can't resist putting this up. So to be in this field, you had to have a lot of perseverance. So he lost his hair in the 44 years between when he wrote that 1972 quarterly report and when he finally got to announce this discovery. And here are a bunch of us just posing for pictures on this really happy day. Thank you.